What's up, Cosmic Explorers? Welcome back to Cosmic Canvas, the channel where we take the biggest, most mind-bending ideas in the universe and break them down into bite-sized pieces of awesome. I'm your host, Mac, and today we're diving deep, like Mariana Trench deep, into one of the most fundamental concepts in physics, space-time. Now, I know what some of you might be thinking. Space-time? Sounds complicated, and you're not wrong, it can be. But don't worry, we're going to unravel this incredible idea together, step by step. We'll explore what it is, why it's so important, and how it's connected to everything in the cosmos. And trust me, by the end of this video, you'll be able to impress your friends, or at least confuse them, with your newfound knowledge of the fabric of reality. So, buckle up, grab your favorite beverage, mine's cosmic coffee, and let's get started. Okay, first things first, what exactly is space-time? Well, imagine the world around you. You can move left, right, forward, backward, up and down. Those are the three dimensions of space that we're all familiar with. We live, breathe, and experience them every single day. Now, let's add another dimension to the mix. Time. It's that constant flow from the past, through the present, and seemingly towards the future. We experience it constantly. But here's the thing. Einstein showed us that space and time aren't as separate as we think they are. Instead, they're interwoven into a single, unified entity called space-time. Think of it like a giant, four-dimensional fabric that makes up the very structure of the universe. It's not just a place where things happen, it's an active participant in how things happen. One of the best ways to visualize space-time is with the classic rubber sheet analogy. Imagine a stretched-out rubber sheet. This represents space-time. Now, if you place a heavy object like a bowling ball on that sheet, it creates a dip or a curve, right? Well, that's similar to how massive objects like planets, stars, and even black holes warp space-time. And this warping, this curvature, is what we experience as gravity. So gravity isn't a force pulling things together. It's objects following the curves and contours in space-time created by massive objects. Pretty mind-blowing, huh? Now let's get a little more technical. Space-time isn't just some vague philosophical concept. It's a precise mathematical model that physicists use to understand the universe. It's described mathematically as a four-dimensional manifold. A manifold is just a fancy math word for a space that looks flat locally, but can be curved and twisted on a larger scale. Think of the Earth. It looks flat when you're standing on it, but we know it's actually a sphere. Space-time is similar, but in four dimensions. Okay, so we know what space-time is, but why should we care? Why is it so important? Well, understanding space-time is absolutely crucial for understanding some of the biggest mysteries in the universe. From the behavior of black holes to the expansion of the universe, space-time plays a starring role in it all. And the key to unlocking these secrets lies in Einstein's theory of relativity. Einstein's theories of special and general relativity revolutionized our understanding of space and time. He showed us that they are not absolute, fixed entities, but are relative to the observer's motion and the presence of gravity. Let's talk about special relativity first. Special relativity deals with how space and time are related for observers who are moving at constant speeds. One of the key predictions of special relativity is time dilation. This means that time actually passes slower for moving objects relative to stationary observers. Yeah, you heard that right. The faster you move, the slower time passes for you compared to someone who's standing still. This effect isn't noticeable in our everyday lives because we don't move fast enough. But if you were to hop on a spaceship and travel close to the speed of light, the difference would be significant. For example, if you took a trip to a nearby star system at 99.5% the speed of light, when you came back only a few years would have passed for you, but decades would have passed on Earth. Another mind-bending consequence of special relativity is length contraction. This means that the length of a moving object appears to be shorter in the direction of motion than its length when it's at rest, Again, this effect is only noticeable at very high speeds. But it's a real effect, and it's been confirmed by experiments. Now let's move on to general relativity. General relativity is Einstein's theory of gravity, and it's all about how massive objects warp space-time. As we saw with the rubber sheet analogy, massive objects create curves and contours in space-time, and these curves dictate how objects move. This is what we experience as gravity. General relativity has some pretty wild predictions, including the bending of light around massive objects, the existence of black holes, and the existence of gravitational waves. And guess what? All of these predictions have been confirmed by experiments and observations. The bending of light was first observed during a solar eclipse in 1919, providing some of the earliest evidence for general relativity. Black holes, once thought to be purely theoretical, have now been directly imaged, and gravitational waves, ripples in space-time caused by accelerating massive objects, have been detected by the LIGO and Virgo collaborations, opening up a whole new window into the universe. So, understanding space-time and relativity is essential for understanding the universe at its most fundamental level. It allows us to explain gravity, predict the behavior of black holes, and understand the evolution of the cosmos. Pretty cool, right? All right, so we've talked about the theory, but what about the proof? How do we know that space-time and all these crazy relativistic effects are actually real? Well, thankfully, scientists are super dedicated, and they have conducted countless experiments to test Einstein's theories, and the results are overwhelmingly in favor of space-time. Let's rewind back to one of the foundational experiments that paved the way for Einstein's theories. The Michelson-Morley experiment. Back in the late 1800s, physicists believed that light propagated through a medium called the luminiferous ether. Michelson and Morley set out to detect this ether, but their experiment famously failed. This failure was a huge clue that something was wrong with our understanding of space and time, and it ultimately helped inspire Einstein's theory of special relativity. Moving on, one of the first triumphs of general relativity was its ability to explain the anomalous precession of Mercury's orbit. For decades, astronomers had been puzzled by the fact that Mercury's orbit didn't quite match the predictions of Newtonian gravity. General relativity, however, perfectly explained this anomaly, providing strong early evidence for the theory. The bending of light during solar eclipses, as observed in 1919, provided another major confirmation of general relativity. By measuring the apparent positions of stars near the Sun during the eclipse, astronomers were able to show that the Sun's gravity was bending the starlight, just as Einstein had predicted. We can even see the effects of time dilation in our everyday lives, thanks to atomic clocks. Scientists have flown atomic clocks on airplanes and compared their time readings to identical clocks on the ground. The results: the clocks on the airplanes ticked slightly slower, confirming time dilation due to their motion. Speaking of everyday life, did you know that GPS satellites rely on general relativity to function accurately? The satellites experience both special and general relativistic effects, which, if not corrected for, would lead to significant errors in GPS positioning. So, next time you use your phone to navigate, remember that you're indirectly benefiting from Einstein's theories. And finally, the detection of gravitational waves by LIGO and Virgo has provided stunning new confirmation of general relativity. These waves are tiny ripples in space-time caused by accelerating massive objects like merging black holes. Their detection has opened up a whole new way to study the universe. So, as you can see, the evidence for space-time and relativity is overwhelming. From subtle effects like time dilation to dramatic events like the collision of black holes, the universe is constantly providing us with new ways to test and confirm Einstein's theories. Okay, we've covered a lot of ground so far. We've explored what space-time is, why it's important, and how it's been confirmed by experiments. But here's the thing. Even with all of our knowledge, there are still many open questions and mysteries surrounding space-time. The biggest minds are still searching for more information about our universe. One of the biggest challenges in modern physics is reconciling general relativity with quantum mechanics. General relativity describes gravity as a smooth, continuous curvature of space-time, while quantum mechanics describes the universe as being made up of discrete, quantized units. These two theories work incredibly well in their respective domains, but they seem to clash when we try to combine them. A theory of quantum gravity is needed to describe gravity at the quantum level, which is essential for understanding what happens inside black holes or at the very beginning of the universe. Developing a theory of quantum gravity is one of the most important goals in theoretical physics today. And then there's the mystery of dark matter and dark energy. Observations suggest that most of the matter and energy in the universe is in the form of dark matter and dark energy, which we cannot directly observe. We don't know what dark matter and dark energy are, but they play a crucial role in the evolution of the universe and the structure of space-time. Dark matter seems to be a type of matter that interacts gravitationally, but doesn't emit or absorb light. Dark energy, on the other hand, is a mysterious force that's causing the expansion of the universe to accelerate. Another mind-boggling question is, why does time seem to flow in one direction from the past to the future? This is known as the arrow of time. The laws of physics, at a fundamental level, are mostly time-symmetric, meaning that they work the same whether time is going forward or backward. However, in the real world, we only experience time moving forward. Why is that? What is it about the universe that gives time a preferred direction? This is a deep and fascinating question that physicists are still trying to answer. And finally, there's the question of the nature of time itself. What is time, really? Is it a fundamental aspect of reality, or is it an emergent phenomenon? Does time have a beginning and an end, or is it infinite? These are deep philosophical questions that physicists and philosophers have been grappling with for centuries. So what's next for space-time research? Well, the future is incredibly exciting. Physicists are continuing to push the boundaries of our understanding of space-time through theoretical research, experiments, and observations. On the theoretical front, researchers are developing new theories of quantum gravity, exploring the nature of dark matter and dark energy, and investigating the arrow of time. They're also exploring exotic concepts like wormholes and time travel, although those remain firmly in the realm of science fiction for now. Experimentally, scientists are conducting ever more precise tests of general relativity, searching for new phenomena like gravitational waves from the early universe and trying to detect dark matter particles. And observationally, astronomers are making observations of distant galaxies, black holes, and other astronomical objects to learn more about the structure and evolution of space-time. New telescopes and observatories are being built that will allow us to see the universe in unprecedented detail. The quest to understand space-time is one of the most important and exciting endeavors in science. By continuing to explore the mysteries of space-time, we can gain deeper insights into the workings of the universe and our place within it. So there you have it, Cosmic Explorers, a deep dive into the wonderful and weird world of space-time. I hope you enjoyed this journey through the fabric of reality. If you learned something new, give this video a thumbs up and share it with your friends. And don't forget to subscribe to Cosmic Canvas for more mind-bending explorations of the universe. What are your thoughts on space-time? Let me know in the comments below. And until next time, keep exploring, keep questioning, and keep looking up.